Hi, and welcome to Allen High School's discussion of chemistry at the pre-AP or honors 10th grade level. If you are not from Allen High School, welcome. We're glad you joined us. Kiddos, my wonderful kiddos from Allen High School, we're getting towards the end. I'm glad you're sticking with it. We're going to focus on really a core topic of chemistry. I know this comes near the end, but it really is a core topic. Now we're getting into some real chemistry. So the first question is, as we talk about thermochemistry and then a little bit of nuclear, is what is energy? How do we define energy? Well, in chemistry, we're going to define it narrowly, as we do in science, as energy is the ability of a physical system to perform work. Now, energy can exist in several forms: mechanical, heat, light, electrical, so forth. And the first law of thermodynamics states that energy cannot be created nor destroyed. But fortunately, it can be transformed. Energy and its transformations have literally transformed your lives. It can be transformed from one form to another. So in batteries, we take chemical energy and we convert it to electrical energy so that you can power your cell phones and our calculators and important things such as that. We've seen already a variety of energy. I hope in 8th grade, 7th grade, you talked about kinetic energy and potential energy. Kinetic energy is energy of motion, and potential energy is energy of position. So if you're up high on a cliff, if a rock is up high and it falls over, it goes from high to low potential energy. Now, ideally, low potential energy is more stable. Now, however, if that was you, so apparently I need to upgrade something. If that was you, you might not be more stable if you fall off a cliff, just saying. But you would be at lower potential energy. All right, so potential energy. There's lists here: nuclear, chemical, and so forth. When we talk about chemistry, our primary potential energy is going to be due to attractive forces. So potential energy is going to be inherent in the bonding structures. All right? So let's start with kinetic energy. It's a little bit easier, I think. Again, remember, kinetic energy is energy of motion. When we calculate it, we'll use 1/2 mv squared. M is the mass. Now we want to stay in SI units, so we're going to measure mass in kilograms, and V is then velocity in meters per second. Now if we do this, we get this derived unit: kilograms meters squared per second squared. And that's our energy unit, and that's known as a joule. Now, remember, temperature is a measure of the average kinetic energy. So, the higher the kinetic energy, that means we have more movement. So, there's increased movement. It's not really phrased well. There is more movement in the substance, more kinetic energy. So if it's a gas in the air, as the air warms up and the temperature goes up, the gas molecules are moving faster. Okay? Now, heat, also called thermal energy, is the transfer of kinetic energy from a substance at a higher temperature or higher average kinetic energy to a system that's at a lower temperature or lower kinetic energy. Okay? Now, when you touch a surface, as you touch a beaker that's exothermic, we've talked about this already, it gets warm because the kinetic energy is being transferred from the substance to the beaker to your hand. And so that heat transfer is felt as systems at high temperature transfer heat via collisions and changes in kinetic energy to systems at a lower kinetic energy. Okay, so we're getting kind of to the heart of this. So let's take a look. The ways we have, and we're not, most of these are a little bit more applicable when you go into physics. So this is a nice transition into physics. But let's take a look at the ways we transfer heat. So we have conduction. Conduction is when there is direct contact between the two substances. Here the hand is in direct contact with the handle on the pot. Convection is when there's a medium in between. So that's what happens in convection ovens. So here you have the heat, and the transfer of heat is through a fluid, and there's some circular motion, and so the heat rises, and then it moves this down, and then heat rises and pushes molecules down, and you have convection. And this can happen in air. This is showing it in water, but it can happen in air as well. As the hot air rises, the cold air comes down, and it begins a cycle. Okay, and then we have radiant energy or radiation. And that's via electromagnetic radiation. And we did that a long time ago. Remember, we calculated a packet, a photon of energy as energy equals h nu. So when the sun is warming us up, that's our radiant energy. Okay? So now the potential energy is slightly different. And I think potential energy is a little bit harder to understand in chemistry than it is in physics. So when we look at potential energy is often called stored energy. And we have to be a little cautious when we think of that, because it makes people think that if you break bond, you release that stored energy. It's not. It's stored energy of one state relative to another state. Okay, so in physics, we typically talk about, and I mentioned this earlier, potential energy being the energy of position relative to a norm. In chemistry, it's either going to be due to that we're going to focus on right now, bonding structures, the attractive repulsive forces involved in bonding, and intermolecular forces, those forces of attraction between two covalent molecules. Intermolecular, I can't write and think at the same time, forces. Okay? IMFs, hydrogen bonding, dipole-dipole, London dispersion. Okay? Now, one of the problems we want to make sure that we clear up here, and I think this goes back to biology, when they talk about energy being stored as in ATP, and when you break a phosphate, you get energy, but you don't get energy from the breaking. You get energy from coupling that breaking with another reaction. That's where energy is released. Energy is released when bonds form, when attractions form. Energy is required to break bonds. What I like to say is it takes to break and it frees to form. Okay. Now, the potential energy that ends up being stored when we react, you break some bonds, you form other bonds. If there's a net release of energy, then it's called exothermic. And that energy can be released. There's another factor involved that we won't talk about, but we're going to focus just on the energetics. That energy can be released and hopefully be available to do work. Okay? If it requires Okay, if it takes more energy to break than is released, so if breaking is greater than the forming, then it's going to be endothermic. It's exothermic if the energy it takes to break is less than the energy required to form. Okay? And we do need to do this gummy bear demo before you get out of here this year. So bring me gummy bears and I'll burn some gummy bears for you. Until then, this is signing off.